doesn't have a webcam. So yeah, I'm really sorry for that. My project is, I'm doing my research in Queen Mary University of London, but also a bit in Imperial College. I have one supervisor there and one here. And the project is funded by the Green Carbon Consortium. I'm working together with Christian and some other colleagues. And in today's presentation, I'm gonna give you an introduction about why are we doing what we aim to do. I'm gonna show present technologies for gas adsorption and storage with a focus on adsorption, because this is the process that we are focusing on, and I can give you more details about this. I'm going to present some carbon materials, and I'm going to explain how we synthesize them via hydrothermal carbonization, consolidating that with some experimental data, and I'm going to finish with summary and future directions. So as I said in the title, our purpose is to adsorb carbon dioxide and hydrogen sulfide, and there are many reasons why we are doing this, and one of them is because carbon dioxide is a greenhouse gas, and it's one of the major causes of global warming. It acts as a blanket, basically it traps the heat and warms the planet. There are many sources of carbon dioxide emission. Many of them are humankind activities, and they are based on electricity generation and heating, as you can see, 44%, transportation, manufacturing, construction, and fossil fuel combustion for other uses. There have been a lot of reports about the carbon dioxide emissions, and different studies reported that since the Industrial Revolution, the carbon dioxide atmospheric concentration has highly increased. So there is a need to do something about that. In parallel, we are also trying to trap hydrogen sulfide, and probably when I'm saying hydrogen sulfide, everyone is thinking about rotten eggs. It's very, very toxic, very smelly, extremely flammable, and yeah, it's not good to have it around. So we are also trying to do something about that. As sources, we can find it in natural gas processing and utilization, hydrosulfurization, and sour gas, and it's poison in biogas and so on. So we have to do something about that too. And of course, there have been a lot of studies dealing with the gas emissions so far. And for example, we have many different methods, including separation with chemical solvents. This process is known as absorption. It's a very common technique when it comes to high volume of gas streams containing both gases that I mentioned before. But the disadvantage of this would be that it involves many solvents. And in this way, it's not a very good methodology. Sorry. Then we have conversion, and for hydrogen sulfide, we mainly have Claus process, which is based on the hydrogen sulfide conversion to elemental sulfur, and involves high temperatures and quite corrosive catalysts. And for this carbon dioxide, we could reduce it either photochemical or electrochemical.
Sabina, just give me a second. Can you stop the recording again? Maybe that will make it a little bit better, because some people cannot hear you very well.
Okay, let me just see how I can stop it.
Just on the bottom, stop recording. And I will record from here.
But I cannot find, so I only have stop share.
Wait, maybe I can. Okay, yeah, continue. That maybe it's better now. I don't know.
Should I start again or?
No, just continue. I'm still recording, but I can make it up.
Okay, but I think I'm still recording. I don't know how to stop that.
Okay. Can anyone, is the audio quality really bad for anyone? Can you write that in the chat? Okay, there's one that hears well. So it might be even not your recording, but theirs. Okay, just continue. Let's see if it works.
Okay.
Whether it works better. Thanks. Sorry.
No worries. Sorry for the bad connection. I don't know if it's from me.
Yeah, I don't know either.
Okay, so I was saying that, okay, here. I was saying that there are many methodologies, and I was talking about conversion, and here for the conversion of carbon dioxide, as I mentioned before, we can do it either photochemical or electrochemical. That could be actually a good way to diminish the carbon dioxide emission. The only problem is that the selectivity and the conversion is not very good. And we also have gas membranes, gas separation membranes, and these are very used. And yeah, the only problem is that they are not recycled. And then we have the adsorption process that is our focus. And here we can have different type of adsorbents. We can have low temperature solid adsorbents, intermediate and high temperature, but our focus is on the low temperature ones, because we aim to diminish these gases in standard conditions, actually in normal conditions at room temperature and normal pressure. So as I mentioned, we focus on adsorption, and as a general definition, probably you already know that this means the accumulation of a large number of molecular species at the surface of a liquid or solid phase in comparison to the bulk. And then you can clearly see in the image the difference between adsorption and absorption. With respect to the adsorption, we have two types depending on the molecules that are forming between adsorbent and adsorbent. So we can have physical adsorption, where the molecules are held due to van der Waals forces. The activation energies are small, is usually completely reversible, and it's not very specific. On the other hand, chemical adsorption is quite specific. The molecules are held due to chemical bonds. We need activation energy, and it's often irreversible. And then we have different type of adsorbents, and here we can have non-carbonaceous adsorbents such as zeolites, metal organic frameworks, amines, mesoporous silica, or carbonates. And they have been tested at temperature lower than 100 degrees. And they seem to work good both for CO2 and hydrogen sulfide, but there is always space to be improved. When it comes to carbon-based adsorbents, which is our interest too, we can have the carbon coming from different sources, a lot like rice hull, bamboo, palm shell, even glucose, and so on. And yeah, our purpose is to prepare them from sustainable resources as cheap as possible. And we also aim to make them to be highly adsorbent for CO2 and for hydrogen sulfide in the same time. So the way how we prepare our materials is called hydrothermal carbonization, and probably everyone here knows what this means. This is a methodology very used in our group. If you're gonna visit our webpage, you will see how my colleagues are preparing their powders via hydrothermal carbonization and use them in different applications. So as a general definition, as Pierre mentioned before, this is the wet biomass conversion technology, which mimics the natural process of coal formation. And the reasons why we choose to use this method is because it operates in mild conditions. We can obtain spherical particles and quite with sizes in the domain of microns. It's quite easy to change the chemical and physical properties by combining the carbon material with different components, such as inorganic compounds. And also, because the surface is highly oxygenated, we can easily functionalize the materials. So when it comes to choose our biomass, here we can have so many sources, so many feedstocks, and I'm not really sure if I can give any advice about this, but I would say choosing the biomass, it really depends on many parameters, such as I would say the first one would be the abundancy, because we need to know that we have a good supplier for our biomass in order to have reproducible results and to eliminate the error of the precursor. So for example, we have some colleagues in Germany which are using brewer spent grains, which is a waste from beer production. And of course, they can use that, and they can be sure they're going to have enough for future experiments, as Germany is producing a lot of beer. So this is going to be always a huge waste in Germany. The same thing could be in England with the tea waste, or everywhere probably with the coffee waste, and so on and so forth. Other parameters could be the chemical composition, for example, depending on the target applications that we we consider maybe we need to have some heteroatoms doped. So in this way, we will consider the biomass which contains the highest amount of nitrogen, or the dopant that we need. So here are just few examples, but biomass is very abundant, so you can choose more or less anything you want or you have. So as I mentioned, hydrothermal carbonization seems to be very good. As I presented before, seems to be the best idea, but there is also some challenges. The main one, the most important one, is that the resulted carbon materials tend to be characterized by low texture properties, low surface area, low porosity. Sometimes they are even non-porous. And this is not good. This is not good for any application, but especially for gas adsorption. And the research community came with some solution to this challenge. The solution would be to combine this methodology with different templating or activation procedures. And depending on the template that we have either soft templating, hard templating, or salt activation. So if we choose to use soft templating method, this involves the combination of the carbon precursor with the template. They are usually polymers, block polymers. They are called bloxamers, and they have this property that at higher temperature, they are soluble in water. They form an assembly, a salt gel assembly, and then the carbon, the hydrochar, grows on top of that. In the end, the template is easily removed by calcination, actually carbonization in inert atmosphere, and we end up with a porous structure. So problem solved. Usually the template and the carbon precursor could interact via electrostatic interactions, or hydrogen bonding, or even covalent bonding. If we choose to use hard templates such as silica, this is called a sacrificial template. We basically gonna infiltrate the carbon into the pores of the template. So in this case, we know the surface area, we know the pore volume and the pore size of the template, and then we choose to synthesize a porous carbon with the same features as the template. So what we do, we mix the template with the carbon feedstock, and then we do HTC. In the end, we remove the template by etching it with acid. We're gonna end up with sponge-like structures, and if we're lucky, we can even control the pore size, because as I mentioned, we know all the porosity details from the template. So this could be the same for the carbon. The advantage of this templating over the previous one would be exactly this thing, that we can control the porosity better, but a disadvantage would be that the removal of the template involves a bit more work, and sometimes we could even not be able to remove the whole template. And then the third method, as I mentioned, salt activation. This is very used because it's quite easy to use it. It's easy also to control the material morphology. The more salt, the larger the surface area. And as a general process, the salts act as molecular templates, either forming ion pairs or salts clusters of minimal free energy. And yeah, we can have different mixture of salts. For example, here we can see that the authors of this study variate from lithium chloride to potassium chloride. And we see that by changing from lithium to potassium, we have a change in the pore size, and also in the surface area, of course, because potassium is larger than lithium, so it's gonna form more mesopores, or let's say maybe more large micropores and the small mesopores, and then by changing to potassium, then the mesopore will be larger. The number of mesopores will be larger than the number of micropores. So the larger the salt, the metallic ion on the salt, the larger surface area in the pore volume. And also another methodology very used in the research community to prepare activated carbons is chemical activation with potassium hydroxide. Everyone is using this because it creates high surface area, and it's not only because acts as a chemical activator, but because different studies propose different mechanisms, and they concluded that actually the chemical activation with potassium hydroxide, it's not only taking place via chemical activation, but it's more like a synergistic effect between chemical activation, physical activation, and the lattice expansion by the metallic potassium intercalation. And this is happening according to the reactions on the slide. You can see that among all the reactions, metallic potassium is generated, and also carbon dioxide is generating. And it's very well known that the carbon dioxide acts as activating agent, creating a lot of micropores. There are many studies which report that their microporosity has been highly improved once they did physical activation in steam of CO2, in flow of CO2. So this being said, here are some images, some state-of-the-art from the methods that I mentioned before. So for the soft templating, you can see the formation of nice carbon spheres, very homogeneous structure. The sizes are quite the same. The morphology seems to be homogeneous. And if you check the table, you will see that surface areas and the pore volume are quite decent. For example, the first line shows a surface area of than 1,000 square meters per gram, which is quite large. So this method is actually good, and yeah, it could be improved. It could be, of course, improved, but it could be used for many applications, not only for gas adsorption. Whenever you need to have a porous structure, you can employ this methodology. And then also for hard templating, you can see that there are pores formed, and this method is very popular for the production of ordered porosity and hierarchical porosity. You can see in the TEM images that the authors reported very nice pores and very well ordered. So if you aim to have an ordered porosity for different applications, energy storage or something, that could be the way to produce them. And when it comes to salt activation, yeah, the structure looks more like a sponge-like structure, or like cheese-like structure, how I like to see it. And yeah, these holes are very good for the gas adsorption. Also, the surface areas are quite large, so this methodology is very popular for the surface areas larger than 2,000 square meters per gram. So in case you need a huge surface area, that could be the way of achieving it by chemical activation with salts. And when it comes to experimental data from our lab, I'm going to give you a short overview of what I've been working on in the past few months. At the beginning, we started with models, with a biomass model system, let's call them like this. So concrete structures such as glucose and fructose. And we did a hydrothermal carbonization of those. And first we employed the soft templating method because of the advantage of easiness in removal of the template. So basically what we did, we had glucose, water, and the template, and we did hydrothermal carbonization followed by template removal. And then of course we tested and we characterized the samples, and we saw their adsorptive properties towards CO2 and hydrogen sulfide. For the salt activation, we chose this time real biomass. We had 3 different biomasses. I'm going to show them later. Again, we did hydrothermal carbonization in the same conditions as previous, and then we activated them with potassium hydroxide in order to achieve the sponge-like structure to ensure high adsorption capacities. And here are some results from our lab. So these materials have been prepared from glucose, and they have been templated with pluronic P123. You can see the formation of carbon spheres, and what we did, we tested the influence of the carbonization temperature, and we observed that by increasing the carbonization temperature, the particles present the same size in the spheres, and also the morphology seems to be similar. They are quite homogeneous, and they are quite stable. We also did some TEM in Stockholm University. We observed the particles better. And then, of course, as I mentioned, we tested their porosity and their properties towards CO2 capture. And again, increasing the carbonization temperature gave us an improvement in surface area, pore volume, and also CO2 capture, CO2 uptake. We observed that by shifting the temperature from 550 to 900, we reached surface area more than 1,000 square meters per gram, and the micropore volume was almost 0.5 cubic centimeters per gram. This means that we managed to improve the CO2 uptake from 3 millimoles up to 7 millimoles in standard conditions of temperature and pressure, and up to 6 millimoles in normal conditions at room temperature and 1 bar. This improvement is because different studies reported that by increasing the carbonization temperature, the carbon structure is going to be oxidized, and then we gonna end up with more micropores. So by larger heat treatment and higher number of micropores, and the presence of micropores is crucial for CO2 capture, especially the narrow micropores, the ones larger than 1 nanometer. In our case, we didn't really have that much narrow micropores, but we had a high volume of the normal micropores, and then we managed to have about 7.7 millimoles per gram CO2. So that were the most important outcomes from the soft templating series. And of course, we are now testing selectivities and stability, and we aim to improve that if possible. And later on, as I mentioned, we changed to biomass precursors. And then in our lab, we used as biomass, we used palm day seeds, guava seeds, and winged beans, which is the shell of the beans. I'm mentioning this because everyone is asking me. And first, what we did, we tested the elemental composition, both of biomass and also of the hydrochar. We did this in the University of Hohenheim, and we observed that all 3 biomasses were rich in carbon, and then after hydrothermal carbonization, the carbon content has been increased. Also, the nitrogen content has been improved, which was quite a good outcome, and this was our goal actually. And later on, after activation with KOH, as I mentioned, we did activation with potassium hydroxide in different mass ratios, and we obtained this sponge-like structure that I mentioned before. And you can see that no matter the biomass, the structure is quite porous, and the materials are mainly made out of big chunks of porous structures like these ones in the picture. And of course, for these ones, we also tested the adsorptive properties for carbon dioxide. We did at room temperature and in standard conditions. We also tested the hydrochars in here, and you can see in the table, the values are quite low in standard conditions. So we didn't really test them at room temperature because it didn't make any sense. But once we activated the powders, we observed that the CO2 uptake is quite good. We managed to have about 5.5 millimoles per gram for the palm date seeds activated with KOH in mass ratio 1:1. We observed that as a general trend, by increasing the amount of KOH, the adsorption capacity is decreasing, and this was actually expected because the more salt, the larger the surface area and the larger the number of mesopores. And our goal is to have more micropores. This was we made it like this just to have a clue and to have a result and see how the results are influenced And then we also tested them for hydrogen sulfide adsorption. These are very recent results we got in our lab. So here we measured many parameters. First, we measured adsorption. We measured the breakthrough time, the time it takes to each sample to be saturated with this gas that we had. We also calculate the adsorption capacity and the adsorption efficiency. And in here, we really got quite large adsorption capacities, up to maybe 45 millimoles per gram. But then probably everyone will say, well, that's great, but it's not always about the adsorption capacity. It's also about the adsorption efficiency, because one material could be really good in absorbing gas, but then it's not efficient. It takes a long time to absorb a specific amount of gas. So for example, as we do it in our lab, we pass gas onto an absorption chamber, and then we measure the outcome concentration. And then if we spend 2 hours in a material, even if the adsorption capacity is larger, the time is too high, and then it's more gas released than absorbed actually. So the ideal material should have a good equilibrium between adsorption capacity and adsorption efficiency. And also the adsorption efficiency is highly dependent on the breakthrough time. So the larger the adsorption capacity, the lower the breakthrough time, the better the material. Of course, these results are still under debate with some other colleagues. We are still doing some measurements. We try to optimize this. I have to mention that every sample has been measured 3 times to make sure the reproducibility. You can see we have some error bars there. And we also measured the commercial activated carbon, named here DARCO activated carbon, coming from Sigma Aldrich. And as adsorption efficiency, we had pretty much 20%. So our aim is to measure more commercial carbons, and then to try to make a story out of our samples and why they variate, how they variate, as you can see them here. So these are just preliminary results. And as a take-home message, I hope I managed to show you that porous carbon materials can be synthesized from a bunch of sources of biomass, and probably you already knew that, but their chemical and physical properties can be tuned according to the target application. We find hydrothermal carbonization an eco-friendly strategy, and that's why we use it so much in our lab. We produce carbon materials with spherical particles. We like the possibility to combine this method with templating approaches, because in this way we can improve the structural features and morphology, and we can have better powders. Yeah, well, this study is based on the idea that carbon dioxide and hydrogen sulfide are not good for the environment, and because of this, we tested the powders towards their absorption, and they seem to present promising results. We have to improve a lot of things, and we hope at some point we're going to be able to use this maybe in industrial applications. And with this, I'd like to thank you for your attention, and I would also like to thank my supervisors, both from Imperial and from Queen Mary. I would like to thank my colleague, Pier Paolo, who helped me in doing HTC from the Biomass, Alex from South Bank. He helped me a lot with hydrogen sulfide setup and everything. Anthony and Sia from Stockholm University, they took good care of me when I was there. I'd like to thank Pablo for elemental analysis, and of course Christian for organizing this. And overall, thank you Green Carbon Project for funding this research, and thank you all for listening. If you have any questions, I'm happy to discuss.
Thank you very much, Sabina. Very nice presentation. So as before, if there are any questions, you can either write them down, or you can unmute and just ask your question directly.
Yeah, well, this is a question I get very often. What can we do with the materials after we absorb the gases on them? Our future goal is to be able to synthesize some powders that will absorb the gases and then maybe release them in a specific atmosphere and maybe react them somehow. Like, for example, to have a powder that will absorb CO2, but then if we put that powder in another medium, then will act as a catalyst and maybe will desorb the CO2 and will, I don't know, enhance the reduction, for example. But that's a long-term goal, I would say. Yeah, that could work probably. I haven't really worked with bacteria. I'm not very sure how they can be used, but of course, I think there is a lot of space to do research in this area, and yeah, that could be a possibility. Thank you for the questions.
So maybe a last round of asking if anyone has a question for Sabina. So I would like to say thank you again, Sabina, for your presentation. And
thank you,
everyone, for participating in the second session. And I hope to see you next week for the third session. And I will try to improve the audio quality until then. So sorry for that. Yeah, and have a nice day.
Thank you, Christian. Have a nice day. Bye-bye.
Bye.